Get to London. That's true. Yeah. Hey, looks like we're live here. Hey, welcome, fellow nerds, to another episode of Between Two Nerds. And as we continue our discussion on switching silicon, I'm Jeff Doyle, and with me is my friend and co-host Jeff Tansura. Morning, Jeff.
Morning, Jeff. Good morning, good afternoon, good evening, wherever you are. Welcome to next show focused on networking silicon. And today we are privileged to host no one less than Israel Meilik, the person behind most of Dune and later Broadcom DNX silicon. And you might not know, but most of your Juniper, Arista, Cisco routers have something Israel has designed.
We can drop a few more names if you
Yes,
want.
absolutely. So one of them would be Ericsson, and this is how we met, by the way, in Yakum many years ago when Ericsson was trying to build first Broadcom-based mobile backhaul router. So anyway, most of internet traffic today is probably passing silicon that Israel has designed. And without further ado, Israel, the stage is yours. Please share with us your wisdom.
So hello everybody. I'm very glad to be here, and I made I believe a nice presentation, and we will go over. I heard it's also going to be a podcast, not only videocast. So I will try to articulate the slides that you may not see while driving. Maybe a short history before we move on to the technical stuff, to the technical and technology stuff.
Yeah, absolutely.
So I started more than 20 years ago it was relatively small startup, Charlotte's Web. We tried to build a core router out of FPGAs. We believe that FPGA will be the fastest to market, and they were big enough at that time to create all the components of a core IP router. Later on, I joined Eyal and Ofer. Eyal Dagan was also the co-founder of Charlotte's Web, and later, together with Ofer Aini, he was the founder of Dune. So Dune, at first, they were focused on traffic management, fabric adapter, and fabric. So meaning doing all the switching of bits inside the router, but they were relying on partnerships to do the network processing. So basically, they were open to all the network processors and packet processor out there in the market. And when I joined, my charter was to add the network processing function into the portfolio of Dune. So at first, I invested like a lot of time. I was working alone like a year on only defining the pillars of the architecture, the functional partition, the system functionality, what we call the packet processing objects, how we do termination, how we do encapsulation, how we do forwarding, all these concepts. And our first product was an FPGA that was outside of what is called the FAP, the fabric adapter processor device. And later on in the Petra, we integrated. So like Guy mentioned, I think you call it like the TM fabric sunk into the network processor. So we integrated, I call it integration, which it is what it is. And so we integrated the network processing function into all of Dune devices. And it is very successful because put aside all the benefits of integration. Of course, when you integrate functions, you save power, area, complexity, all of that. Putting that aside, the fact that you work on a daily basis, meet in the cube next to you the TM architect, and on hourly basis you discuss how to partition the functionality, what information to pass from here to there, what will be the best format to expose some information one to the other. The fact that this is integrated, it's in the same small team, this is making a big difference. So I think let's go over the presentation that I make. And I followed Jeff highlights and try to go over the topics that Jeff wanted to cover. And I call it the era of merchant silicon router, because indeed, if you look like 20 years ago, there were almost no merchant silicon that could reach all the platforms, all the big vendors. Indeed, EasyChip was maybe, I would call it an outlier in the sense that they reached a wide deployment relatively. I mean, also they were limited to some specific type of system, to some specific type of market segment use cases. We will see that our target is the widest possible. So we don't narrow into one zone, one segment of the market. We try to cover as many segments as possible. So let's see how we do that. So let's go very, very briefly over the agenda just to see what we have. So some introduction on what it takes to build a market-leading routing silicon. I will give my perspective of what it takes. Then some history. When I say history, this is not like a story, but more of you will see the evolution of the devices in terms of bandwidth, technology, power, etc. Then I will lay out some of the network processing design considerations, the points that I see as key points for designing network processing. Then I will go over some industry trends that we see and that we are putting into our devices, how it is different than past devices, how it is evolving into the future, some key design points in the products that we make, and the last slide is a little bit about the future, what I can expose. Feel free to interrupt at any point. So let's move on. Okay, so how can you build a market-leading routing silicon? And I believe Jeff mentioned it a little bit, but our silicon is indeed at every segment of the market. You will start with the access, the PON or the fixed line access, go to aggregation, to the metro, to the backhaul, front haul, mid haul, X haul, of course, core router and backbones, peering routers, into the mega scalers. Basically, our reach is everywhere. So what it takes to be in all these places and to be successful in all these places. So our top concern is to be in full alignment all the time in what the industry and our customers wants to do, how they see their networks, how their networks is structured, and what is important to their network. So these are discussions that you have to invest in like all the time, keep track of what is going on, and it's not easy, because these guys are very busy. They are not happily, quote unquote, waste their time. So you have to come with your own innovation, your own technology lead to make them, to get the interest out of the other side and make them believe that you can answer their needs and build the best network for them. So the interaction with all the mega scaler, with all the big service providers, with all the customers is a must. Um, Second is, and this is something that we realized like few generations back, that the world is the main, I would say, concern or pain point of our customer is becoming the power. Power is limiting our customer ability to build the networks that they want. Um, they care, I would say, even less about the cost than the power, because the power, if they don't have enough power into a given location, they will not be able to build the network. So we have to be focused about how we do the best power efficient devices possible. I will share some key concepts that we use. One of them is, of course, modularity. And this is something that we keep in mind from the architecture phase all the way through the design phase, the RTL design, the physical design. And this is really a key point in our thinking and in our approach. Another dimension is the ecosystem. Especially for a merchant silicon, you have to work in creating a rich and big ecosystem. And this is really a work. You have to, so we discuss and cooperate and have initiatives with so many companies, starting with the smallest. It's I don't want to offend anyone, but there are the if you quantify it by the market value, there are the $1 million or millions or $10 of millions startups. There are the 100 million startups, and all the way to the MSDCs, to the big OEMs like Cisco, Nokia, Ericsson, Juniper. So we work relentlessly with all of them. You have to build all the software layers, starting from the driver. So we have our own driver, but we also working on all the open drivers like the SI layers, open and the proprietary operating systems, the system vendors, if it's ODM or OEM. We work and collaborate with all of them to provide a very rich and large ecosystem that any potential user can pick and choose whatever form or size or operating system of his choice.
And looking at my personal history, I was always amazed how, our DNX team is really, really small team, just a couple of people. And each time there's innovation in the industry, we would be sitting together talking about beer EVP, and I still remember we spent 2 weeks in Israel in Yakum talking about how EVP and was doing all the programming through different databases. So the team is so hungry to details, to new technologies, and this is how they really build really good products that are innovative but allow you to build on existing architectural pillars, just evolving right parts.
Yeah, and really we don't have we don't say or work less with anyone just because he's small. We evaluate the innovation, the technology. This is what is driving us, not the dollar value of each and every one. So let's go over, like I put here. I didn't put of course the numbers for the devices that we are about to announce. So on the right side you have devices that are called next generation Jericho and next generation Ramon. You will soon hear about them, but for now let's stop at last year, where we announced the Jericho 2C Plus. So looking all the way from the Petra B, which was accompanied by the FE600, this was 2010, and just to put the scales, the Petra B was a 200 gig device, line card device. The FE600, which is our fabric device, maybe I will say a few words. So the way Dune technology works is that we have a fabric device, a line card device. The market name for that is starting from 2015 is Jericho, and then we have generation 1, 2, 3, and so on and so forth, and derivatives. And the fabric device, which is basically the most efficient switch possible. What it does, it just takes cell from one port to another port. There's no decision making. You don't need buffer there because everything is scheduled. So this is the most efficient switch one can build. And so with these two building blocks, you can build what is called a single stage system, meaning you go into one of the Jericho devices, cross the Jericho device sends spray cells into the fabric devices. The fabric devices send it back to the destination Jericho, which reassembles the cells back into packets and send it out. So this is not the topic of my discussion, but I will say a few words. So first of all, there is always the discussion about cells versus packets. I think this discussion is more or less not relevant, and I will say why. The modern cells are as big as packets. Okay, so it's not the ATM 53 byte cells. this is long ago. So the modern cells are as big as packets and as efficient as packets, or even so. It enables you the perfect load balancing, as simple as that. With packets, you cannot do perfect load balancing because you have to keep a flow selection over the same links. Whereas where you go with the cell-based fabric, you do the perfect load balancing. You just send the next cell to the next available link. And again, maybe you will take a separate discussion with Golan, which will be happy to go over all of that. Golan is our TM and fabric architect. So these two components, you can create a big system which is single stage, or you can go even to a multi-stage system. A single stage system is typically the topology is a closed topology, if you are familiar with that. It's like, you have a row of line card devices, a row of fabric devices, and then you have like a full mesh of connectivity between each and every one of them. This is the classic topology. And you can build also multi-stage topology. So if we look on the Petra generation, these systems were in the order of terabits. So you would look on a chassis, it was typically few terabits, depending on how many line cards you would have. On a line card, you can have 1, 2, or sometimes even 3 or 4 line card devices, like the Petra or the Jericho. So if you have like 8-slot chassis, you have anywhere between 8, 16 Petra to, let's say, 32 Petra. Likewise on the Jericho devices. What is evolving now is that we move into a disaggregated distributed chassis, which is basically you take what used to be the line card and the fabric card, and now you package them in a pizza box format. And instead of a backplane, a passive or active backplane that is using traces of copper or other conductors to route between the line card and the fabric, you can use short reach optics. Now, so if we go to the Jericho 2, Jericho 2C Plus systems, we already see petabit scale systems. Okay, so it's an increase of 3 orders of magnitude over like something like 11 years. I believe this is very impressive. Because again,
for our listeners who might not understand the context of cell versus packets, so if you are on a multi-PFE or multi-ASIC system, you hit ingress ASIC, you need to traverse fabric, and then you hit egress ASIC. So what Israel was talking about is how do you split what comes in to transport it over the fabric. So 2 technologies in general available. You can solidify, meaning you cut the incoming pipes into reasonably small, or actually looking into latest silicon variable size cells, and then you reassemble them at egress, or you use packets or frames, depending of which layer of XML we are talking about. So Guy didn't want to really go into this. Practically, as Israel said, Broadcom has been using solidified fabric, so using cells since day one, and there are many advantages to that. Most important one is predictability, right? You know exactly the size of the cell, you know what you expect on another side, so your delay jitter product is exactly the same for each cell, which allows you to do reassembly without buffering, without due delay due to things coming at different times.
So maybe just for those who listen to the podcast and don't see the slide, I will just say that on the left side, we see 2010 Petra B 200 gig device on 65 nanometer technology. And on the right side, we see the Jericho 2C Plus, which was released last year, 2021, on 7 nanometer technology, and it is a 14.4 tera device. So it's a 70x increase over 11 years.
So looking at the slide, you clearly see the how we get more bandwidth. We shrink, right? We go from 65 nanometer on the left all the way to 5 nanometer on the right. We know that 3 nanometer technology is being typed out. TSMC 3N is, we know how it looks like. We probably know how 2 nanometer devices look like. We don't really know how smaller devices look like. So what do you think?
I was working at Intel in 93. And, at Intel you have various lectures. And one of the lectures was, are we nearing the end of the silicon, 93? And so the lecturer said, I believe we have at least 5 years. So I believe we have at least 5 years.
Okay.
I believe that we will. But by the way, like Shraddha is the name of the. So yeah. Shraddha, I think that she listed the issues that we see with the technology. The technology is not evolving as it used to be. Routing on the new technology is not improving like the transistor size. The memory is not improving like the transistor sizes. So it is becoming harder to squeeze more out of the silicon. And what you see is that I believe this is a common, I think all the major players are reaching the it's called the reticle of the product, meaning the maximum size silicon that they can create, and trying to squeeze more out of the technology. And yeah, the options are probably moving into other dimensions like building. So we already have 2.5D technology with the HBM interposer, and I believe that in the coming years we will see 3D, meaning one silicon above the other, and they are talking directly one to each other. So this is the coming technology. The problem is that it is very, very expensive. It is very expensive, and also it is very hard to dissipate all the power.
So what's your view on integrated optics and how it's going to play?
Yeah, so optics integration is, I mean, it's a no-brainer. This will be in the next generation, I believe, of all the vendors. You will see it. There is no way around it. And other forms of integration. So a good example of an integration that we made is, for example, moving from the Jericho 2 to the Jericho 2C+. We integrated all the security engine into the device. So just keep in mind that on a board, on a customer board that is doing security like MACsec or IPsec or TunnelSec, you used to have like tens of discrete devices providing the same functionality as a single Jericho 2C+. So the saving in power is huge. Just, I should have prepared maybe a slide only on that. This simple integration, which is really not, technology breakthrough, but again, you have to work with the right team and to close very closely the interaction, the functional partition, how you transfer the information, etc. This integration of the security acceleration into the device is saving huge amount in the total power of the system.
Absolutely. I can tell you that the exabits of data live in data centers, and as you probably know, any bit leaving data center in any of hyperscaler is using MACsec between data center gateways, and next stage devices. So ability to save power here saved those companies really billions of dollars.
Right. Okay, so if we were talking about power, this was a great intro to this slide. So what you see here are measured power of our devices in similar conditions. And you see the trend. So again, the technology is not, if you just do the same, let's say, logic, you will not see this saving, because again, the like moving from 7 nanometer to 5 to 3, it's not saving so much on the power. So you have to think about other ways to save power, better integration, optimize, do a modular design that you can use in many ways and not save by putting extra silicon functionality that may be achieved in other ways.
So you probably heard that number of countries have denied Microsoft, Amazon, Google building new data centers. And the answer is very simple. It's actually not the country or government itself. It's electrical supply, it's power supply that cannot supply enough power for 1.5 gigawatt large data centers. So it's not money, it's definitely not the space, it's inability to deliver this amount of power that becomes real roadblock to building more efficient, larger data centers.
So I don't know if you heard about it, but I read an article last week saying that both Microsoft Azure and AWS, they had plans to build new data center in Ireland. And now because of the issue with the gas and the power, they are not able, they decided not to go with these plans. And they will not, at least for now, build these new data centers. So what we see here, for those, again, who are driving, we see the power from the Petra B all the way to the Jericho 2C+. And this is power per 100 gig. And you see that the Jericho 2C Plus is about 15% of the Petra B power per 100 gig. Again, this is not the device power, this is device per 100 gig. Okay. So moving on, and let's discuss a little bit what are the design considerations when you want to build a new network processor. So I put here some illustration, and the point I am trying to make is that there are many complex operating points, and you are trying to create a product that meets and basically excel in as many as possible of these operating conditions. So just listing the changing parameters that you have to take into consideration. So of course you have to build the same or similar architecture for different bandwidth points and interface ranges. So in the DNX portfolio, typically in a given generation, we have between, like, I would say, 4 to 6 devices that have the same architecture, but different interface and bandwidth points, or interface ranges and bandwidth points. We have devices that target the highest bandwidth and the most or the highest bandwidth interfaces, and as many as possible. And we have mid-range devices, and we go all the way to devices that are working in a cell site or very small access point. So this is one consideration. Then you have to, of course, you also have the trade-off between efficiency versus simplicity versus programmability. It's not a big challenge to do a fully programmable device, but then it will be less efficient than it could have been. When you go to the most efficient, it is not always the simplest device, because then you have to configure it in a very delicate way to achieve what you want. So this is a triangle of requirements that we always struggle with, and we try to be as programmable as needed, as efficient as we can be without losing the simplicity and the programmability. So this is a triangle of contradicting requirements. Then you have the database scale, and this is a big challenge, and I will cover it in some few more slides. And we are targeting, as said, basically all the big networking market, meaning starting with the access. It may be a PON or fixed line, moving into the aggregation, the metro, the front haul, the mid haul, the back haul, the core, peering routers, data centers, the different layers of a data center interconnect, and try to be as efficient as possible and also as fit as possible to each and every one of these.
Yeah, I think what's important to understand, you often see this kind of messaging, my device supports P4 or OpenFlow or whatever next generation of behavior languages is, and it's fully programmable. There's no free lunch in fast path. Programmability comes at cost, which is usually speed, power consumption, and price. And engineering work is to analyze these trade-offs, right? Like our friend Ross says, if you haven't found trade-offs, you didn't look deep enough. So there is no free lunch. You really need to understand what part needs to be programmable, what part needs to be fixed, what needs to be run to completion. And all this, as Israel explaining, they are all contradictory requirements. So finding this exact point that still makes your device efficient but programmable while allows it to evolve is the golden engineering of silicon.
Yeah. And yeah, so basically this, going back to my first slide, you also always have to be in touch with the field and see what is needed and what is the best way to serve it. Again, to build a fully programmable device, we can do it. The question is, will it be the best device? And probably it will be best only for some very, very, I don't want to say niche, but very, very specific application. And you try to, and this is also for our customer benefit, you try to cover as many as possible, because it also offload the customer investment in the technology, the customer investment in learning. So saying that, I think that Guy also touched on that, saying that my device is P4 is not enough. You have to be familiar with the device capabilities. It's P4 by itself leads you to the design of Barefoot, and other devices that are using P4 are using some extensions to the P4, and even with with a barefoot device, you have to be very familiar with the device to actually get the most out of your P4 code. Because if you just write a naive P4 code, you will probably exhaust the device resources very, very fast and not reach the most out of your device. So this is maybe the last point here, is we want to minimize our customers' software investment. We invest a lot in backward compatibility, and you see that we have a trends of families of devices. We try to keep code consistency, for sure within the same family. So looking on the Jericho 2, we have, as I said, like 6 different Jericho 2 devices in different speeds, in different scales, in different port configurations. All of them will use the exact same code. So the same code that you write to the most powerful Jericho 2 device will run on the weakest, quote unquote, Jericho 2 family device. I think you said it. I put it in other words. We are looking for an architecture that enables all the, I would put here, target application. I mean, I am not trying to do applications that are, not relevant. We are trying always to tune and calibrate the architecture to enable all the applications. So this was just maybe an overview of the consideration. Maybe let's look on some trends that we see in the market, okay? And then say how we react to that. So what we see is that over the years, the frame size, the average frame size of the application, or the requirements for the average frame size were changed dramatically. So if you were 10 years ago designing a new network processor, packet processor, any pipeline, not coming with a full wire speed for 64-byte packets was like a crime. Okay, if you would say my device is not incapable of running 64-byte packet at wire speed, it was a big no-go. And as we progress, we see that our customers themselves and the application that they are using are increasing the average frame size, and as an effect, the efficiency of the network is increasing. Our device power is decreasing, and like on every device that we define, we are trying to discuss this point with every potential customer to understand what they see in the network, what are the trends that they see, what is the current requirement. And you can see by this graph that if on the Petra B we were supporting 64-byte packets at wire speed, as we evolve, I think from, so this is the processing rate per 100 gig. Okay, per 100 gig of interface, the Petra B used to do 150 million packets per second. And if you go to the Jericho 2C+, the number is about 40 million. So it's less than a third of the Petra B. And we continue to monitor this and tune the device. We have to be at least as the customer need. But if we were just, covering our eyes and say this is what we need to do, 64-byte wire speed, then probably we would build bigger than needed not inefficient devices.
And kind of to elaborate on this, the watt per bit is decreasing. However, since we upgrade, total amount of power required is increasing, and which each generation is probably X2. So we are still, hitting the roadblock of power efficiency and ability of external power provider to provide this amount of power. So all of this is greatly helping, but not to the degree that we can start building larger data centers.
Yeah, it's a race.
Yep.
Okay. So a few other trends, I call them, put them all under network protocols. So one trend that we see is that the header decap and encap, if we look like 10 years ago, it was in the order of tens of bytes, no more than that. And as we go into modern networks, not all of them, but some of them are talking about hundreds of bytes of packet modification, meaning that the difference between the incoming packet and the outgoing packet may be hundreds bytes that we remove and construct different, or just remove, or just construct new headers. So this is one trend. Another trend is what probably everyone is aware of. This is the growing of the internet, especially the RIP size. We see exponential growth. So if in the past it was mainly IPv4, in recent years it is moving to the IPv6, and we see that the IPv6 is starting to get the exponential growth. So this is another trend. Another new, I would say, very highly focused area in recent years is everything that is related to telemetry and instrumentation. And by that I mean any type of technology, protocol, application that is tracking, collecting information, statistic about the health, the state, what type of traffic is running in the network. So there are many protocols. Of course, you have all the legacy, S-Flow, NetFlow, etc., but you have many more. You have in-band telemetry, which is like every node that the packet is passing would put some portion of metadata into the packet. This is one option. You have multiple ways of passing this information to what is called the collector. I put here like two options. One is to stamp it over the packet. You see, I don't know if you see my cursor, but this is the upper. It's not a drawing, it's a photo. And also you can do what is called postcard, meaning every node is sending like a postcard for that packet or for that flow to a collector. So it's not carried over the packet, but once the packet is reaching some node that is tracking this flow, then a postcard will be sent to the collector. And then the collector needs to collect all the postcards to retrace the packet or the flow to know where it went and what happened in different nodes. So this is an area that we see basically across the industry, the mega scalers, the service providers, all type of networks. They are all into telemetry and instrumentation.
So to elaborate on that, we are planning a separate podcast focused on in-band telemetry, where we will in-depth explain all the possible way of doing it. So embedded data, which is Israel explain as you put more data as you traverse the network versus postcards, where each device sends the data to the controller, versus newer version of this where you send it back to the sender. This is work I'm pretty much spending each day a couple of hours on. So stay tuned. We'll talk about inbound telemetry and new applications for this.
Yeah, this is an endless topic, basically.
Yep.
Okay, so what do we do in our devices to cover all these challenges that I listed before? So this is like an illustration of the pipeline. You see on the top the ingress pipe, on the bottom the egress pipeline. A packet is typically traversing the ingress pipeline on one device and then going to the fabric and traversing the egress pipeline on another device. But this is, again, putting aside, this is how the packet is handled in a distributed system. What are the two concepts that we put here? So you see the title is Sharing is Caring, and we put some two main resources that we try to take it to the extreme. The first is the Modular Databases, or the MDB. This is basically what we are trying to do. Actually, I have a slide on that, so I have a slide on both of them, so I will just say one of them is the Modular Database. The other one is a matrix of programmable elements. Both of them are accessed from all the pipe stages and are serving all the pipe stages. The pipe itself is a systolic pipeline, a programmable systolic pipeline. And it is like everyone is taking as much resources as it needs from the shared pool. So let's dive a little bit into that, into the modular database. So you see some illustration of that, meaning there is a shared pool of, it's called memory, but actually it's a memory blocks, thousands of memory blocks, and all the pipe stages can access the same pool to create different databases. Now, on the drawing above, you see different use cases, and I just used three colors to illustrate like three big databases. Let's say the forwarding, the classification, and the encapsulation database. When you look on different types of application, you see that they have different partition of the databases between them. So what you want to achieve is, with the same memory, be able to serve different requirements over different installation of the same device. So again, you take the same device, the same amount of memory that you have, and in one use case, you want the biggest forwarding database. And all the other databases, you want the minimum. This is just an extreme example. You take the same device, the same technology, and you move it to another location where you want very large classification databases, not the IP routing tables, but all the customer classification rules and databases. And yet another place where you have a very rich tunnel scheme where you need a lot of memory to create sophisticated and very heavy tunnels like SRv6 or other types, or segment routing, MPLS. So all of these use cases are served with the same device, with the same amount of memory. And what is even more important or stronger is that from the programmer point of view, the way the memory is partitioned is irrelevant. You program just the functionality, and if you have a lookup, you don't care what is the size of the database that is sitting that is answering that lookup. This is not part of the program, the size of the database. This is opposed to other architectures where the pipe functionality is tightly coupled with the database. So whenever you change the functionality, you have to change the compilation of this code into the pipeline, and it creates you a different mapping of this code to different allocation of the device. So we see it as a very, very strong point. It helps our customer, to invest much less time in, working on different use cases of the same device.
So translating this into networking language, the closer you are to the edge, the more state there is. So if you're on the core, most likely you've got a bunch of MPLS tunnels you need to switch. Requires reasonably low amount of resources. You do use superflex, but besides the point, as you move towards BNG or peering place, where you start taking full BGP tables from 2,000 peers, suddenly you're looking into millions of routes in your fiber, right? You are looking into 6 levels of QoS for BNG. This is where your state is becoming really, really huge as compared to basic routing. So ability to use same device, you said, in different places just by changing profile rather than recompiling, rebuilding, forklifting is a huge improvement from usability and actually reusability perspective.
Yeah. Okay. So let's touch on another sharing. So we look again on this systolic pipeline, and we say with our rich programmable systolic pipeline, we are trying to cover all the use cases that we are familiar with. The problem is that networking is evolving all the time, right? So for that, we introduced the elastic pipe. This is an extension of programmable elements that is sitting next to the pipeline and can serve any pipe stage. So the concept is that this is a shared pool, and every application will take as much as needed. So in this example, let's say I need an additional MPLS termination stage, which I don't have in the systolic pipeline. One option is to recycle the packet and go again over the pipeline. Another option is just to extend this specific stage with few more programmable elements and do the additional functionality in the PE metrics. Now, again, time fly and there are new requirements. So let's say now you have a new forwarding protocol. Again, you need new functionality, which probably your pipeline is incapable of supporting. So again, you go out from your pipeline to the PE metrics, and you add this new functionality. So we see this PEM as a huge success. This is give you future-proof. Typically on the first rounds of the device, if we have bugs, we are able to fix the bugs in the PEM. Our customers takes it to really extremes. I mean, most of the functionality that they do, we are not aware of. And this PE metrics is really a very strong tool in our tool suite.
And I think our favorite example here is Vxlan. If you remember when Vxlan came in, there was number of, I wouldn't call it vendors, but devices that requires other recirculation, or it was often implemented as disabling one port on the switch to route Vxlan. So ability to have this additional logic and implement new functionality without respinning the device, which in case of Trident resulted in Trident 2 Plus, as we all remember. That's the only way I would deploy today. If I know that in 2 years I need to deploy something new and I would need to do complete respin, probably I wouldn't even consider this kind of device.
Yeah. So there are many examples, and again, in some cases, so for example, Cisco were driving SRv6, and they developed SRv6 over Jericho. We don't have this microcode. I mean, they developed SRv6, and they were the first one to introduce the working SRv6 using the programmability on the Jericho device. Last point that I will touch, and this is what we called massive concurrency. So in many cases, especially in network processor, they say, yeah, we can support any protocol. We are, whatever you bring us, we can support. The problem is not only supporting all these protocols, but supporting them all in a single image. I mean, you don't want your customer to reload a new image whenever you decided to use another protocol or application in your network. You want to be able to have all of it available at any time and just use it simultaneously without any performance impact. And this is like a major or key point that we are insisting on every DNX device, on all the Jericho devices.
Yes, sir, I have a technical question to you. So last week was an amazing week for silicon builders and enthusiasts. We had both hot chips as well as hot interconnects in the same week. So it was an amazing week in terms of amount of information shared. So Juniper actually presented the Express 5, which looks very much like Jericho. However, they also mentioned that they use Bloom filters to increase the scale of routes. Can you comment on this? If you cannot, that's perfectly fine.
So I'm not familiar. I saw some presentation about the Express 5. It's really looked like a very interesting device. Indeed, it resembles a lot the Jericho line. Specifically, you say Bloom filters for what?
For LPMs. So because.
Oh, okay. So we examined and we actually use Bloom filters for other applications, not for LPM. I believe that our LPM technology is pretty solid and efficient. I don't think we can squeeze much more out of it. I mean, in terms of bit per entry, it's probably, and as said, I'm many years in the industry. I don't remember such an efficiency for LPM. But this is a good point. I will gladly look into that and see. But in any case, I don't think it will for our implementation. I don't think it will be a big improvement. Maybe there is something to squeeze out of it. Yeah, interesting, but it is an impressive device.
It is, absolutely. So for those who are interested, it was presented by Chang Hong Wu at Hot Chip last week. So the next question here, we know that number of routes in DMZ is growing. We are about to hit 1 million routes anytime from now, even before. But this is not what concerns us. It's really the V6 table that's going to grow because disaggregation is happening. We're all trying to optimize the way we route. So the size of FIPS is going to become a limitation again. How do you think we can solve this problem without just throwing more memory on it?
Okay, so we have some ideas that we are working with. I think what is missing is because again there are trade-offs which I'm not sure the industry is already mature enough to accept. Okay, I will give you an example. Think about the slide. Let me go back to that slide. Yeah, this slide. So, like 10 years ago, no one was willing to hear about a device that is not supporting wire speed of 64 bytes frame, right? But as the industry matured, now they say, okay, the average frame size is much bigger than 64 bytes. So I think that I know that we have solution. We started to discussing this solution with some of our customers, and I believe that we will go in that direction. It's a matter of time. But for sure, we will be more efficient in the IP tables.
So trying kind of to translate what you said into more concrete terms. So you think that by increasing minimal packet size supported, which is perfectly fine for most people, going from what's supported there around 200 bytes, maybe 370, 390, it will allow you to move some part of lookups into algorithmic LTCMs and increase amount of power efficiency without actually throwing more hardware resources on it.
No. What I am saying is that, like in the past, there was some rigid thinking that you can never work with a lower packet rate than the one required for 64-byte packets. I'm saying there are some trade-offs. I don't want to get into the technical details of that, but there are some trade-offs that you can do that will the end result will be a much more efficient routing table, meaning in silicon power mainly and area. But it will be a trade-off. There will be some trade-off, and this trade-off, I think that if we discuss in person under NDA, I can explain you the ideas that we are examining. And I'm sure that there are other ideas, but for sure this will not stop the revolution.
Okay, and we will do so absolutely, and obviously.
Yeah.
Thank you. Let's continue.
Okay, so this is my last slide, talking a little bit about the future. So, by the way, one thing I want to I didn't articulate enough is the cadence of our execution. You see, in about every 2 years, we are coming with a new device. We take the new technology, we improve the architecture. So we are relentless, and we will keep to be relentless because this is a never-ending race. So I cannot share exactly because we didn't, declare it yet, but expect big news soon. We keep monitor and like I said, meet and interact as much as we can with all the players, our end customers, the vendors, and we examine all the trends to see how we can do better and how we can give the best device to the market needs. not just the best device, the best programmable or the best, I don't know, frame modification device. Because selecting and enabling the right trade-offs is the key to a winning architecture. Yeah.
Okay, so I'll ask you same questions I ask all others. Your view on the evolution of SerDes, encoding of SerDes, and where do you see the most issues?
So just looking on the history, again, I'm not a SerDes expert, but in the recent 25 years, it looks like the cadence of SerDes evolution is steady, more or less. And I don't see the roadblock yet. So it is hard to foresee, and especially to foresee the future, but I don't see in the near future any hard stop.
So let me ask you the question differently. I think we always had a roadmap, at least for 3-4 years, right? We knew much in advance that we need to go from NRZ to PAM4 when we hit 25 gig per service, right? However, I think we do know that 200 gig SerDes are going still to be PAM4. There's nothing better, even so, some propose PAM6. But after that, at least from where I can see, it's completely black. We actually don't know. So any predictions in this area?
Yeah, so it's not necessarily on the single SerDes, but maybe co-package optics will give you some better integration, some better cost power trade-off. So very short reach versus medium reach. I think you will see more innovation because it's there is a demand. The industry, you see, what is going on with the data centers, with the AI, ML. We see the need for connectivity. The industry will supply this need.
Yeah, but without going into too much of this, we see again the set of requirements that stretch technology in different direction, right? You need to put FEC introduce latency. You don't put FEC suddenly. The connection is not reliable enough. So I'm really excited to see what's coming and how we're going to solve all those issues.
Yeah,
but we will talk about it maybe a year, 2 years from now.
Yeah, but just one point. I think that the buzzword of latency is a little bit misconception in the sense that this is not the only parameters that you need to consider. There are other ways to improve your flow completion time, not only the single stage latency.
Agreed.
So I'm less concerned about the additional latency that the FEC introduced. There are other ways to improve.
Great. Jeff, any questions?
I have no questions. I think this has been a fantastic session, and as usual with me, I've just sort of been in learning mode through the whole thing.
Yeah. Learning is good.
Absolutely.
So it seems like we are going to have another session specifically on Broadcom DNX with Israel and Golan. And I would like to thank Israel. It's been absolutely amazing.
Thank you, Israel.
Many people are going to be very happy with it because it's close to impossible to get any information about silicon. So thank you so much. And we are looking forward to seeing you again soon.
Okay. Bye-bye.
Thank you, Israel. And thank you to everybody that joined us. And as usual, please like us on Facebook and follow us on YouTube. And we'll see you again soon.
Okay. Bye.